So now we're going to look at one of the cornerstones in signals and systems, and that is that multiplication in the time domain is equivalent to convolution in the frequency domain, and multiplication in the frequency domain is equivalent to convolution in the time domain. So we'll go ahead and we'll prove one of these analytically, and then we'll go and we'll have a graphical representation of it and we'll look at it in MATLAB. So analytically, if we had a function x of t, when we Fourier transformed it, we give us a function x of I omega. If we had a second function h of t and we Fourier transformed it, it would give us h of I omega. Now we know that the convolution operator y of t can be written as x of t convolved with h of t. So when we convolve these x of t and h of t together, we get this integral from minus infinity to infinity of x of tau h of t minus tau by d tau. Now we're interested in what happens whenever to this convolution operator whenever we Fourier transform it. So we'll go ahead and we'll Fourier transform this. So the Fourier transform y of I omega, well, it's the integral from minus infinity to infinity of some function times e to the minus I omega t by dt. In this case, the function that we're wanting to find the Fourier transform is the convolution operator, which is this function here. So we just put this function here into the Fourier transform. Now, what we're going to do here now is we can take the x of tau out of this first integral, because tau is not a function of this factor t, so we can put it in a bit outside this first integral sign. So we're going to have the integral from minus infinity to infinity of x of tau, and then at the end we'll have our d tau, and we'll have what's left over in the centre. Now again, we'll just use the substitution as I mentioned before. This is, you'll see this, it's quite prevalent throughout a lot of the proofs that you do here. So if we say that p equals t minus tau, so we can replace this with value of p. So we can therefore say that t must equal p plus tau, and also that dt must equal dp. The value of tau is just a constant, so it just disappears. So substituting these into this here, we're going to have your x of tau and your d tau. You're going to have the t minus tau as your value of p. You're going to have your dt is equal your dp, and the factor of t there is your p plus tau. So it means you can split this out, and this function e to I omega out into the two components. So there's an e to the minus I omega p, and there's an e to the minus I omega tau. So when we do that, we get our integral from minus infinity to infinity over x of tau e to the minus I omega tau by d tau, times integral from minus infinity to infinity over h of p e to the minus I omega p by dp. So this here is nothing other than our x of I omega. That's a Fourier transform, and this here is none other than a Fourier transform over h I omega. So we can see then that the y of I omega is equal to x I omega plus h I omega. So that really shows us that whenever we convolve these two functions x of t and h of t in the time domain, it's equivalent in the frequency domain of multiplying the two functions together. So that's our little analytic proof. So let's go ahead and we'll look at it graphically. So here's a graphical representation. We've taken out a square function called x of t. We have another function here, square function, we'll call it h of t. So we're going to convolve these two functions together. Now whenever we convolve these functions together, we get a function g of t. Now we'll see that in a minute whenever we look at it in MATLAB. Now if we were to Fourier transform this square function, we would get the sinc function. Again, if we Fourier transform this square function, we would get the sinc function. So our contention is that if we were to multiply these two functions together in the frequency domain, then we would get this function here, which would be a sinc squared function. And we're saying that if convolution in the time domain is equal to multiplication in the frequency domain, then this function here, if I was to find the Fourier transform of this function here, I should just get this sinc function. Okay, so first of all we'll go and have a wee look at the convolution of these two square functions, giving us this triangular function. And then we'll go ahead and we'll have a look at the multiplication in the frequency domain, giving us this function. And finally, we'll show that the Fourier transform of this function is indeed this sinc squared function. So we're going to convolve these two functions here, x of tau and h of tau. So we form the h of t minus tau, multiply it by our x of tau, and then when we integrate it from minus infinity to infinity, we get this little triangular function g of t. So let's go and we'll see that in MATLAB. So finally, let's go ahead and we'll look at the Fourier transform of the triangular function, and we'll see that that triangular function, when it's Fourier transformed, gives us this sinc squared function. So let's look at that in MATLAB. So we can see that if we had a triangular wave in the time domain, when we find the Fourier transform of it, we get this sinc squared function. So that's as we expected to see from the previous slide. So let's have a wee look at this in MATLAB. So let's look at the Fourier transform of our triangular pulse, and we'll see that it produces that raised cosine. So a triangular pulse is given by this little function here, and it runs from -2 to 2, and it's symmetrical about the origin. And we're doing it from limits of -10 to 10. So that's available in the resources section. You can go and copy and paste that in. And here's the output from it here. We'll turn it around in this direction. You'll see that it's actually it's a purely real function, and you can see that it looks like the sinc function, but it doesn't cut down below the axis, it gets raised above. Okay, so it's a raised sinc function as we expected to see. So let us summarise the main points in this video. We've seen that convolution in the time domain was equivalent to multiplication in the frequency domain, and we worked through the examples there in the previous couple of slides. Now we can also say that multiplication in the time domain is equivalent to convolution in the frequency domain. So we can say that our g of t equals x of t times h of t. Then in the frequency domain we'll have x of I omega convolved with h of I omega, but of course there's an extra factor of 1 upon 2 pi in it at this point here. Okay, so that's all there is for this video, and I'll get you on the next video. Goodbye.